Hello everybody. So let's today talk about iterative methods of solving linear system of equations. And here we will just actually talk about Jacobi method and Gauss-Seidel method. And so let's get started. So what I have is I found one very nice code from internet or implementing Gauss-Seidel method, and this is very concise and very short. And why I don't have Gauss-Seidel, don't have a Jacobi method, but Gauss-Seidel only. Here is that Jacobi is just a simpler version of Gauss-Seidel, you can say. So I think we don't need to bother with both of them. Just Gauss-Seidel is enough. So let's get started. So where I found this code is here in Trinket. There's an example of this code. This code just I copied to my slider here. So what's Gauss-Seidel method and what does it do and how it works? So I also found from internet one lecture slides on the methods. So I just using this nice presentation, I will just use few slides of this presentation to explain. So we have a system like this, just normal linear system. So Jacobi method, iterative method. So what it does is it goes step by step. So in any iterative method, we give some initial value. So for all of this x from x1 to xn, we just randomly or with some prior knowledge we can assign. Okay, we can guess. Okay, they all can be 0 or some of them can be some numbers. So anyway, we can assign some initial values to them, and then we will solve the system in some way. Then we will get new value of that this x's, and then we will insert that x's to repeat the procedure. This iterative process will be just continued like this. I hope it's so. Here, for example, usually we assume that all of the x's are 0. Zero. If you have some prior knowledge what their values can be in real life applications, usually you know in what range the values should fall. So you can just guess some value. So usually it's guessed as zeros. So if you believe that these x's are zeros, then you just insert them here and then calculate x1. For this Jacobi method, so yeah, you will your initial case will be all zeros, and you will put all zeros here. So this part essentially will be 0 for the first step. So then you will get x1. So for x2 same, xn same. And after the first iteration, first doing all this for n, you will get values for x from x1 to xn, a different value. And then in the next step of the iteration, you will use these values which are found here to insert here and find x1 and x2, xn. So if we repeat this process many times, usually we get to the solution, which we can find by using inverse matrix method or lower and upper triangular decomposition, or the other methods that we use to solve the linear system. And Jacobi method is this: just insert, and find these values, then insert again, just this. And for Gauss-Seidel method, it's a bit more advanced, it's a bit more smart, because so you will use, it's a little bit not clear, but okay, I will go back to Jacobi version here. So In the first step, you will put all zeros for these x's, and you will get x1. And for calculating x2, why you should use x1 as 0? Because you already guessed it can be something different than 0 using this first line. Yeah? So just use the result from this first line here and just plug in the result here. And you will get the x2, which is more up to date than the Jacobi method, which uses already, it's still x1 as 0. Yeah? And for x3, the same. You will use x1 and x2, which are calculated from these equations. And then you will continue until xn. For xn, you will not have here zeros, but the values calculated from the equations above. And you will reach to xn, then the process will start again from x1, this equation here, but this x is, as you already know, they will be already calculated down here. And yeah, the same process will repeat. This is Gauss-Seidel method. How do we, this x's will converge to the solution, or the solution that we usually find by other methods. Yeah? And how do we make sure that it converges, and how do we check that? And if we are using iterative methods, we should stop our algorithm somewhere with some criteria. So we will discuss these things using the Python code. I will explain it in the code. The one thing that I would like to mention here is that for this Gauss-Seidel method, Gauss-Seidel and both Jacobi method, there is one essential important requirement, which is, here you can see the wiki page, diagonally dominant matrix. Diagonally dominant matrix is a matrix where the diagonal elements are in absolute value larger than the sum of the absolute values of the elements in the same row. So for each row, the diagonal element, for example, here this one, will be, the absolute value of this will be larger than absolute values of those in the same row, the coefficients. Yeah. So if these diagonal values are large, very large, then the Jacobi and Gauss-Seidel methods will converge to the correct result. So this is the fundamental theorem that we should keep in mind. If you have, for example, if you have here 0, do you know what will happen? So here you use this A11 as divisor, yeah? And then you will fail because you cannot divide number by 0. So in this case it doesn't work. So the higher this diagonal element, the larger this divisors will be, so the more stable your result will be. So we just should keep in mind. So in case some these diagonal elements are too small or 0, then we should probably interchange the rows to come to a stable matrix. Okay, so now let's go to the Python code and let's see how it's implemented. So this Gauss-Seidel method, this is very short, just like 9 lines of code, and that's it. And this lower part is just example, ignore it at the moment. And this is essentially the code, and this is just explanation and copyright stuff. And so we will just the Gauss-Seidel, the function will be taking the function arguments m and x0, x and max iteration. So m is a matrix. It's not just only the matrices of A's. It also includes B, and B we don't need to put B into the left hand side and make it negative. We just combine them. Just A matrix and B matrix. B matrix as the last column of this combined matrix. Yeah? And for x0, it says default value is none. So none means for x0. X0 means initial case. Initial case, as I told, usually we take it as zeros. So we would zeros. So we can give them value, either values, or we can just give none. Then it will be implicitly assumed that they are zeros. So this is the second argument. For third argument, also there's a default value. Ips means we will iterate many times, and in the end, this x's which are calculated in these steps will be very close to each other if we are successfully doing it. But they will most likely be not equal. For example, x1 in the 100th iteration will be very close to x1 from 99th iteration, but they will not be equal. So if x1 doesn't change much from iteration to iteration, we can say that it has converged to some stable value, or it has converged to the solution. When it converges to the solution, it doesn't need to change because it's already on the solution. It will be just staying there. So then we don't need to require them to be exactly the same from iteration to another iteration. You know? So we can tolerate some discrepancy, difference. So in this case, we will be fine with a difference. If this x is we will talk about exactly what difference, but difference between x's will be within minus 50 degree of 10. So if it's smaller than that, then we say okay, they are the same. X's have converged, so we will accept the value as solution. No? And that's the third argument. And next argument is about max iteration. So if this iteration continues, if this x doesn't converge to some specific stable value, then this iteration will continue. So probably we would like to limit that. If it continues maybe 1,000 times or 100,000 times, and if it doesn't find any solution, then we should just give up and we should change our methodology. And for this case, it's very humble. It's just 100. And if you, after 100 iteration, if you cannot find x's which are close to each other, or the solution very close to the solution, then you should just give up, stop it. Then yes. So how it does? So for if here ln is the first dimension of it calculates first dimension of the matrix M, our extended matrix, which includes both A's and B's. So it means essentially N means number of rows here, right? And then if x0 none, if it's equal to none, then we just make x0 equal to n times zeros. So 0 times n will be just 5. For example, it's 5. It will be 5 zeros, yeah? And we will get this value. Or otherwise, if it's not none, if it's given by the user, then it will be x0 itself. So why I was saying here that it will implicitly assume it as 0. This is because here is one line which handles the case if it's 0, if it's none. If it's none, it's not a number, so it will have some problem. So we will replace this none with some number here, here zeros, and then we will it will be our the x0 will be our initial guess, yeah, and then from initial guess we will get to the point where we will save x. We will our first case. Okay, let's say first case or guess. Our guess will be first case will be this. So from here we will continue. Here is just to demonstrate it will print where what values are there. Okay, we can comment it actually now. Okay, I will comment it and we will use it later on. Now it's not important. Then we will iterate through this number of max iterations. Yeah, the actions we will do will be limited by number of actions will be limited by this number, and then we will go to number of rows here. We will loop through rows. So essentially, it is doing this calculation: first row, second row, nth row. It's trying to calculate all of them one by one using loop. So here is it's summing up the M is matrix, the A matrix, A and B matrix, and it's multiplying by this matrix element by X elements, and for all of the its range n is actually this A matrix is itself quadratic matrix, it's assumed, and the row number of this equals column number. So here we can say it's column number, and for each column then we multiply this column element or this elements of this by the coefficients. So I starts from 0, so for first column this will be 0, and first this essentially will be multiplication of each x initial values of x is given here 0 for the first iteration, yeah, by the coefficients here, but it skips one value. If I not equal to j, it means for the first row it will be 0, so it will not take first column, and for other columns it will just do this multiplication. So we are essentially finding this component here we are calculating this component for here, and here we are escaping this. If 2 for Python case it will be 1 not equal to 1, here 2 then other coefficients with other x's will be just multiplied. Then we find this, we will name it as S, this part, and then we from coefficient of xi, the ith row that we are concentrating on, then this is n means last. This is last column actually. So it means in the last column we have these b's are in the last column, so we put the b's here, and these b's are here. So here we skip it b because the j goes until n, but it doesn't reach n itself, so it leaves out the b last column. No? So here we have last column, and then we add this s. We are here subtraction, looks like subtraction, but here adding because here we already have negative number. And we divide it by this diagonal element, this 2, 2, 1, 1, and n, right? Then we will loop through all row. Then once we finish looping through all row, you should remember that it's just the first iteration. Just for the first iteration, we have gone through all the rows. So just once we have done this, then we will do it many times. Maximum we set it here 100, and then after doing the loop, we will compare our resulting x1 value with what we have in the initial condition or prior to x1. Yeah? So if this difference is actually if this difference for each of I, for I is this row number, so if each of I is the difference between two iterations, yeah, initial value and then the current one, is less than epsilon, and here 10 to minus 5 degree, and for each row we compare these two values, and if all of them are within this limit, then we will return, or we will stop the loop, and we will give x1 as the solution because it's so close to initial value. Yeah? If not, then we will redefine x0 as x1, and then from here we will start using this x1, which is already the solution from the previous round, as input to the next round. Then we will repeat the solution again, then we will compare x0, x1. As x0 here means the solution already from previous round, then x1 here means solution from just current round. Yeah, so I guess it's clear, and we will continue. Then if it reaches 100, and if it doesn't find anything, it will go out of this loop and it will jump on this, so there will be error, so that solution doesn't converge. So that's it. Then we will the result that we will get will be x1, which will be already the solution. So let's see with some example. I have prepared a simple example. So just this we will just import numpy, and then here will be our M matrix. So I just called it N. Yeah. So our matrix is this 3 to 3 part will be A matrix, and this last column will be B matrix. So I can just show it in different way. A and B defined separately. A0, I call it B0. So A matrix is here, B matrix is here. And so the solution of this system, if we use, okay, let's say inverse matrix method. So let's use linalg enough A B. We should use input that. Oh yeah. Cool. B0. Yep. A0. So the solution is 1 1 1. So if you have x1 to x3, then each of them will be 1 1 1, and that's the solution. And now, what if we use our Gauss-Seidel method? It should give us 1 1 1. So let's see. Let's run this file to define this function. So I will just click F5 here, then we run, Control L to clean console. Then now, what's our A? Our A is good. Now, so let's say solution, Gauss-Seidel, and then we will insert A, okay? And for x0, okay, let's leave because it has default value. So there's no error. So seems like our solution has been found. So it's very close to 1. This is very close to 1, and this is very close to 1, and if you actually see, this is like below 10 to minus 5 degree, right? So that's our Gauss-Seidel function seems to be working. And now let's see how it's actually working. So this loops are how it's working, how they're working. So for each iteration, let's print out how they are doing. So let's put here, let's just put here x1 the result, how it's doing, huh? So let's try to redefine it, and we will use the same. So it first starts with this, then goes and comes to the solution here. Then the last value should be equal to this one, but it is not, because we are it has already been returned. So if you put it above before returning, I think we can see the last value of the iteration. So let's just do let's then print out the solution. So this one equals the solution. So this using print function, we can see how the iteration is doing. So also to inform, just for interest, let's put here iter, so we can say which iteration, which step it's going on. Okay, so here it is the iteration number 0, 1, 2, 3, 9th. So 10 on 10th iteration, we have reached the solution, and then our function has stopped and it gives us the solution. So as you can see, it's not exactly 1, but very close to 1. So let's just play with some numbers. For example, let's change it to, we can actually solve them. Let's say 0, 0, 0 as initial value. Okay, same initial value. And for x we can give minus 10 and solve it. So okay, this is even more precise than this one. As you see here, nice. So after 19 is 17 iteration. So because we made this precision smaller, this needs to run more. However, let's say we cannot run 17, we just run 10. So in this case, let's see what else. So there's an error. So the solution doesn't convert because we are limiting it by 10, and by the 10th iteration it's not yet close to each other. It's not it doesn't know the solution 1, 1, 1, but the difference between this and these two are so small that it's below this precision, but by the 10th iteration it's not yet there, so it gives an error. So that was it. So let's start from something. We can get rid of these things. Let's start from some different initial value. We can actually start from anything. So let's try. So just after 8 iterations. So it's, you see, first it was 1, this, then it became almost 1, and it's converged. So let's say 20, 50, 200. So how many iterations? So just after 13 iterations it's coming down. So it's very, sometimes it's quite mysterious that 2 linear systems of questions, you just put any values and you come to some precise solution. This is interesting. However, if we dig the theory, this is not very interesting because matrix eigenvalue, eigenvector decomposition things will show that what kind of matrix will be stable and will be able to converge to its solution from any position. Yeah? And now, for example, we have our matrix A, or this matrix A0. This is, as you see, this is 7, which is larger than sum of absolute values of these two, and this 5 is larger than these two, and 8 is larger than sum of these two also. So this is, as I mentioned in the beginning of the lesson, diagonally dominant matrix. For diagonally dominant matrix, it's so good that it can converge. However, let's try to change the game a bit to make it more interesting. So let's exchange the order of these two. You will know why I'm changing. Maybe you already guessed. So let's say it's A1. Define. It's A1. A1 is this, and let's try to solve it by our dot. So you know we didn't change the equation, so it should give us. So let me just convince you that the solution should be the same, 1 1 1, because we didn't change anything, just change the order of the equations. We should actually, you know what? We should also play here as well. Now let's just change A1 itself. We don't have to write it down again. Okay. And P0 is this, and we just exchange the position of A matrix. And now let me show you, it's still the solution is 1 1 1. A0 and B0, A0. So, of course. Why? Because we should change the order of these two as well. Good, find 1 1. So interchanging the row doesn't change the solution. So for Gauss-Seidel method, will it change the solution or not? Let's see. Initial value we just can keep it as 0. So let's start with this. Oh, solution does not converge, and as you see here, it has the iteration. It's on this 100th iteration already, but in the beginning it started as this, and it became infinity, then became none. So why is this? Because here, if you see this warning, divide by 0 encountered in double scalar. So let's see why it's being divided by 0. So on the second equation, if you see this diagonal element, so to calculate x2 or second x, we will subtract this times x3 from here, then this times x1 from here, then we will have x2 multiplied by 0, and we divide all this on the right hand side by 0, and we will get infinite. And then our our calculation fails. So this shows us that it's very important to have this diagonally dominant matrix so that we can reach a reliable, we can make reliable calculation. So that's it. And yeah, why don't we use just inverse matrix method and other decompositions instead of this iterative methods? So iterative method is in large applications, large cases with so large matrices and things, and when you cannot invert matrices, you can just use this. You just plug in some value and iterate again. Then you will have some idea. It can diverge away from the solution, or it can converge to that solution. So that's the value of iterative method, and this is Gauss-Seidel Jacobi method that we discussed today, and it will not be limited by this simple example. It is so powerful that it's used in many places. So thank you for your attention. Bye bye.